Welcome. I'm glad you could join us for our presentation on seismic resistant design for developing communities. This presentation centers around the project we did for Hope School in Mbita, Kenya, where we built a 60-bed dormitory that is seismically resistant. I'm David Mukai. I'll be one of your speakers, and the other speaker will be Adam Block. Before we start, we're going to introduce ourselves.
Hi, my name is Adam Block, and I am currently working as a reservoir and development engineer for Oventive in Denver, Colorado. I graduated from the University of Wyoming in 2017 with degrees in mechanical engineering and energy systems engineering. I participated in Engineers Without Borders throughout the entirety of my career at UW. I served in a number of different capacities, including as secretary, president, and Kenya program manager. And perhaps most applicable for this discussion, I participated in the Hope School Dormitory Project. From inception in our first assessment trip all the way throughout implementation, where we actually constructed the project throughout a summer in Mbita, Kenya.
David Mukai. I'm one of the faculty advisors for EWB at the University of Wyoming. Go Pokes. I originally became part of EWB to be advisor for this dormitory project, and then eventually I became faculty advisor for the entire club. I traveled with the team on this project all the way from assessment through implementation, and I hope you enjoyed this presentation on seismic resistant design. First, I want to set some expectations for this talk. There's no way in 30 minutes we'll be able to teach you how to do seismic resistant design. Instead, we'd like to cover these 5 learning objectives for this talk. First, do you need seismic resistant design? And if you do, my advice is, and the requirement really is, you will need a structural engineer to be on your team. Second, if you do need seismic resistant design, I'll go over what the first steps you're going to take in the process of getting the project going. Next, I want to cover what will likely be the solution to your building, which will be confined masonry. Next, I will go over some resources that you'll could use for your project. And finally, we'll go over some lessons from our project. So the outline for this talk, or the map to reaching these objectives, is as follows. We're going to start with an introduction to give you the background of our project in Mbita, Kenya, and to talk about the seismicity there. Next, I will try to convince you that you need a structural engineer if you're designing in a seismic zone. And then I'll go over the likely first steps in your project, which will be schematic design. And within that, the 3 things you're going to have to do is first identify the applicable design codes. Second, discover the seismic hazard for your site. And finally, probably you will choose confined masonry as the solution for your building. Then we're going to shift to the lessons we learned in our project in Mbita, Kenya. And then I'll end with some resources for you. This talk is meant to be interactive, and it's hard in this virtual environment. So what we're going to do is periodically throughout this talk, I'm going to stop, and I'm going to give some links for you to some Padlets where you can respond and put questions or remarks. And during the course of the days after the conference, Adam and I will go and look at those and respond to your questions. So first, let's start with the introduction. This project that we did was for Hope School in Mbita, Kenya. And what they were trying to do was to transition from a day school to a dorm school or a boarding school. And we came on board to help them construct a dormitory for their students. During the design process, we uncovered that the seismicity in the region where we were building was roughly equivalent to the seismicity in the Bay Area where San Francisco is. And that really affected our design. Here you can see the distance from Laramie, Wyoming to Mbita, Kenya. It was quite the travel ordeal to get there. And our clients were Hope School, and these are some of the students, the staff, community members at Hope School. But the real client in all of this were the children. Adam will talk about this more later, but sadly, when we were there, 25% to about a third of the students are orphans because of an extremely high HIV incidence rate. And this led to some very difficult societal pressures, particularly on the young women here. They were very vulnerable orphans. They would orphan vulnerable children. In the end, this is what we made. We constructed a 60-bed, seismically resistant dormitory. And on the right, you can see our work crew, students working alongside with the community, making this dormitory. But what we really think we made, or what we hope we made, was a difference in the lives of these students. Let me talk a little bit about seismic design experience. And if you can get one thing out of this talk, it's that you will need a structural engineer on your team. This will be someone with seismic design experience, and if possible, find somebody within the country that has local experience, but that's going to be a function of the country. Not all countries have local engineers with seismic design experience, and so it'll depend on your country. If you are working in Guatemala, where many of our projects are, they have excellent engineers that have seismic experience, and so you should be able to find local expertise. I do research in seismic design, and I often visit Japan in my research. And amazingly, while I was in Japan, in my little research group, was a PhD student from Guatemala. And he lives very near where our current Guatemala project, which is not a building, a water system project, he lives there. So I'm certain you can find local experience in Guatemala. Why do you need a seismic design expert? I'm going to fly through these slides so we can save time at the end for Adam to talk about lessons learned. Let me go over, if you've never looked at this before, if you've never had a senior design course, the design process for any project. Typically in an engineering design project, and especially for a building project like ours, there's 3 phases. There's the schematic design phase, the design development phase, and the construction documents phase. And in our case, we also had the actual construction phase. And what I'm going to argue is that you will need a structural engineer for all 3 of these phases. In the schematic design, you're going to do 2 things. You're going to come up with the design criteria and the design concept. So here's the concept we used for our dormitory. You really will need structural engineering expertise to carry out these 2 tasks. In the design development, what you will do is you'll develop 3 structural systems. If you're doing a building, you'll do the vertical load resisting system. You'll design the lateral load resisting system. This is a system that will resist the earthquake loads. And you will also design the foundation system. Again, in all 3 of these tasks, you really do need a structural engineer, and especially you'll need someone with seismic experience when you do the lateral load resisting system. And finally, when it comes to making the construction documents, because this type of building will probably be complex enough that you'll have to put this out to bid, you'll need to develop plans and specifications. And in both cases, you will need a structural engineer. And in addition to that, you likely will need local expertise. So on this photo on the left, that's a consultant that we hired in country to help us put the project out to bid and to select the best contractor. And that contractor is on the photo on the right, the man in the middle, that's Walter. He was our contractor, and he learned a lot in our project. He learned how to do this confined masonry technique, and he liked it so well, he said he's going to use that technique for his future projects. So let's talk about the design process. The design process will depend on your project type. And so you can't ask questions for us now, but we have uploaded these PowerPoint slides. And so you can download that and you can access this link. I think that's a bit much to type. But if you go to this link, it'll take you to a Padlet where you can describe your projects. And this way we'll get an idea of what you're doing. Okay, the next part of our talk is to talk about your likely first steps in this project. You've gotten a structural engineer on board, and one of the first things she or he is going to do is walk you through schematic design. And I'm simplifying here, but the two main things you're going to do in this schematic design when you're developing the scheme, you're going to define the design criteria, and you're going to come up with a structural design concept. And so you will likely, as a chapter, be able to participate in these two tasks. Okay? The design criteria. What you need to do in the design criteria is find out what the governing building code is, come up with the design load criteria, in particular the earthquake load criteria, and look at any special considerations or requirements. The first thing you're going to have to do, and you could probably do the legwork on this, is to figure out what the governing code is locally. And it might be specific to the city, not the country. Once you do that, it will be useful. A lot of these codes are based on either our code here, the IBC, or the Eurocode, or maybe some other codes. And probably your best bet to identify the governing code is to talk to a local engineer. Once you identify the building code, if you have a local engineer, the local engineer will be familiar with it. But in our case, we did not have a local engineer, and the in-country code was not the same as what we did. It was more like the Eurocode than the IBC. And then we had a difficult decision to make. Would we design it according to what we know how to do because our engineers were US trained engineers? Or would we try to find somebody from Europe who could help us with the design? And in the end, we chose to design according to our code here in the US. The second part of the schematic design is to come up with the design load criteria. And in terms of the earthquake, what you are going to need to find are the ground acceleration values. Your structural engineer will be able to walk you through what you need, but essentially what you need is what's known as a seismic hazard map. And your friend in doing this is a group called Geohazards International. And there's the web link. And what I like to do is walk you through their website. So here's the Geohazards website. This organization was so helpful to us in our project. I'll post the links at the end, but when you go through here, you can go over their strategy, how you can make an impact. And what was very helpful for us were these resources here. And what I would do is give them an email, describe what you're doing, and they'll point you in the right direction. So both of these things for the design criteria that you're going to do in schematic design, so it'll be design criteria and load criteria, are heavily functions of the location of your project. where your project is will define what building code you're using, and where your project is will define what your seismic hazard is. And so if you could, oh, I see a typo here. We can fix that. So if you could, go to this second Padlet, and it'll have a map, and using the zoom tool, you can get in where your project is, and you can put a pin there where your project is. That'd be fun. We'll go back later and see where all your projects are located. Okay, so we are moving right along. I really am trying to save time at the end for Adam to tell you about lessons we learned. We've gone over the introduction here. I hope I've convinced you that you need a structural engineer for your project. And your likely first steps, I said, was going to be schematic design. We went over the design codes and the seismic hazard. Next, the structural concept that you're going to use is probably going to be confined masonry. As I said, the structural design concept, which can be in a developed country, you're going to choose, should I use a reinforced concrete building or a steel building? Should the lateral system be shear walls or a moment frame if it's concrete, or should it be a moment frame or brace frames if it's steel? We didn't have those options, and you might not as well. And so the structural design concept that will probably be your solution, and we were pointed towards this direction by Geohazards International, is confined masonry. And the advantages of confined masonry are they use readily available materials. It is very earthquake resistant. It's been used very successfully in Europe and in South America and in Southeast Asia. And if Geohazards International was your friend for determining seismic hazard, EERI will be your friend for confined masonry. And let me walk you through their website. Again, I'll post the links to all these things at the end in a Padlet. But EERI, or the Earthquake Engineering Research Institute, they have a confined masonry network. And you can go through this website. And one of the cool things that they link to is the World Housing Encyclopedia. And this has confined masonry guidelines, everything from construction to design, and materials in several languages to help you to work with your community to adopt this technique. And so EERI, and the links will be in the Padlet, is your friend for confined masonry. Now, let me show you a little bit about how we implemented confined masonry in our project. Here's a photo of our project in Mbita, Kenya, under construction, and it illustrates the basic concepts of confined masonry. First, you construct walls without the concrete around it, and these walls are toothed, so you can see the offset running bond here. And you construct the walls first out of the masonry. And the nice thing about confined masonry is you don't need really, really high strength bricks, but you do need reasonable strength bricks. In our case, the fire adobe bricks that were available were not strong enough for us, so we ended up getting stones from a quarry. And so these are very nice blocks, and so you make the walls first and then the reinforcing cage. And after the masonry wall is constructed, then you pour the concrete around it. And this sequence of doing the wall first with the toothed construction and then pouring the concrete around it makes it very, very earthquake resistant. This technique is very common in developing countries, but not on the continent of Africa. And so this was a new technique we introduced. We felt very good about it because another organization was building a building in country. We got in touch with their engineers, and they also were using confined masonry. So we were certain this was the right solution. And this involved the use of structural engineers, and our structural engineers happen to be Duncan and Aaron. And so if you happen to come across this talk, Duncan and Aaron, thank you for your work on this. And here you can see our final design, the construction documents that we put out to bid, and here is what it looked like when it was constructed in the end. And so hopefully I've achieved the objectives so far. What I've been trying to hope is that I've convinced you that you need a structural engineer. I went over the first steps you're going to need to take. You need to get the design criteria, which will be finding the building code and identifying the level of ground hazard, probably with assistance from Geohazards Inc., and then picking your structural concept, which I think will likely be confined masonry, and I've highlighted that to you. I've been giving you resources all along, and at the end, there's a Padlet, and there'll be a slide with all the links to the Padlets, and that Padlet has links to everything I've talked about. And so last, I've saved some time so that we can talk about lessons from our project. And I think the best person to do that is Adam. And so Adam was our president at the time of EWB. And let me get rid of this. And so I've asked Adam to discuss these things here, to talk about why we made this dormitory, to give you some background on the societal issues we were confronting, talk about the design issues and the construction issues. And we decided this would be best done in an interview. So I'm going to interview Adam, and he'll address these questions. And after the interview is over, I'll come back and wrap up. Adam, thank you for taking time to answer these questions. This is probably the best part of the presentation. You talking about what went on the ground during the project, during the design part of it. I'm sure the students really want to hear from another student. So let me get to it. Adam, can you tell us about the Hope School Dormitory project? Why did the community want to build this dormitory?
Mbita, the community where Hope School is located, has been ravaged by HIV/AIDS. When the dormitory was constructed in 2016, over 25% of the local population were confirmed carriers of the disease. Mbita is especially susceptible to HIV/AIDS because of the sexual requirements placed on women within the local fishing industry. Sex is often used as currency, allowing women to purchase fish to take to the market and feed their families. As a result, countless children have been left orphaned to fend for themselves. With few employment opportunities, these children often turn to the same industry whose malpractices took their parents' lives, and the cycle propagates. Hope School aims to provide these orphaned and vulnerable children with a chance at a better life. And by partnering with Hope School, we at EWB designed and constructed a dormitory to provide the orphaned and vulnerable children with a safe space to live so that they can pursue their education unencumbered by the burdens and stresses of fending for oneself in the streets of Kenya.
You mentioned you were involved in this project all the way from initial assessment to final construction. And along that path, one of the steps is design. So what were some of the design issues with this project?
All right. Quality control was a major concern both in material and labor. Based on information gathered during our assessment trips, we knew how challenging it would be to maintain high constructional standards during implementation. We compensated for this by developing a conservative design that'd be able to withstand the risk associated with questionable materials assembled by unskilled laborers. To make things more complicated, Mbita is located in a seismically active area, so a structural design that would be able to withstand a seismic event was critical. With Dr. Mukai's expertise and experience in seismic structural design, he was able to guide the team to confined masonry, which is a robust approach to structural design often implemented in the developing world where seismic activity is a concern.
One of the unique things about this project, Adam, is that we actually saw it through construction. And this was a major project. It took 3 months to build, And again, thank you for spending an entire summer in Mbita, Kenya, seeing this building constructed. Can you go over what some of the construction issues were? There are always issues, so I'm interested to see what you highlight as the ones that stuck out to you.
I think when implementing any project, the health and safety of the workforce and neighboring community are paramount. In the United States, we have agencies such as OSHA to help ensure that companies are effectively protecting their employees. In Mbita, we found no such organization. There's no such thing as workman's comp, and we were laughed at when we brought up the idea of insurance. It was the role and responsibility of EWB to ensure what we could, within our power, that no one was recklessly endangering themselves during the implementation of our project. We provided PPE to the workers on a number of occasions, and albeit temporarily, introduced a culture where safety is discussed and considered throughout each major task. In general, a major challenge for the team was working together with our general contractor to evaluate the local construction standards to elevate the local construction standards to something more acceptable to our team. Only one first aid event occurred during the implementation of the dormitory, which is definitely a statistic that we can be proud of. A second issue that was not immediately apparent but festered throughout the project was the lack of desire by the key stakeholders to participate in the construction of the dormitory. Many of the key stakeholders of our project, primarily relatives of the children of Hope School, were unemployed. We worked together with our general contractor to offer employment to members of the community, but no one accepted. We were told by the school president that in their culture, it is degrading to work in construction. And so the lack of investment by the community was a large red flag for us at EWB. Many members of the community would come up and ask us for money daily, but no one we encountered was willing to work for it.
And Adam, as you know, we have these technical issues of design and construction, but often, as is the case, the societal issues are probably the biggest issues in a project like this. Can you talk to that? What were some of the societal issues that stood out to you that we had to address?
I think before engaging in any project, it's important to define success. As EWB, we set out to construct a dormitory and we were successful in that feat. But what good is a dormitory if it's unoccupied? What good is a dormitory if 1 year later the entire school staff pick up their bags and leave because your in-country partner is corrupt? As engineers, we're capable of providing anyone with any material good, but that does not mean that everyone will benefit from what we have to offer. It's not enough to evaluate whether or not you can design and implement a project. A full cultural, anthropologic, and sociological assessment must be conducted at the micro and macro level to determine the likelihood that a project will be successful and sustainable. Privileged by our Western status, regardless of the actual size of your pocketbook, you're viewed as wealthy in Mbita. During assessment trips, we were constantly approached by people as young as 3 years old who would say, "Mzungu, give me money." Mzungu means white person, by the way. And when we would respond, especially with young children, I think it was apparent that this was the only English that they knew. At first, I didn't think much of it. Individuals who have money everywhere are constantly asked upon by those with less. We did it ourselves in order to raise money for the project. And what I did not realize until the implementation trip, however, was that it is a social responsibility for the haves to give to the have-nots in Mbita. We were told that if you have, I quote, "you must give." It is not socially acceptable to have more than someone else. The issue was exacerbated when one of our students, members of Engineers Without Borders, raised money to buy a home for one of the teachers, but not for the president of the school whose house had recently burned down. We, of course, could not raise money to build a house for everyone, and as a result, resentment built up throughout the community. It's another story. One time I came across a woman giving birth in the gutter along the side of a dirt road. with a group of about 10 people standing there just staring at her. Seeing me approach, someone from the crowd said, "Mzungu, come help." I, as the white person, of course, was expected to be the one to do something. I ran and got help from a local friend who called a car to come and pick up the woman and take her to the hospital. By the time I got back, the woman was holding her child, lying in the dirt with the umbilical cord still attached. When the vehicle arrived, I barked orders at two of the bystanders to help me carry the woman and her child into the back of the vehicle so that we could take her to the hospital. After we arrived at the hospital, nurses came and assisted the woman out of the car, cut the umbilical cord, and escorted her inside. The next thing that happened kind of dumbfounded me. I was instantly asked for money by the man who helped me transport the woman to the hospital. They asked for money for themselves and for the woman whose life had likely just been saved, asking me who's going to pay for the hospital bill, with the expectation that I would. When I said no, I wasn't in the position to give them money, they became quite agitated. I think it became instantly apparent that the men who helped me were not looking out for the child or for the mother, but they were looking out for themselves. The driver of the vehicle tried to charge me an outrageous rate for transporting the woman to the hospital, and at that point, I was a little lost for words. What kept on coming into my mind was, what would have happened to the woman and her child had the Mzungu not come along? Would anyone have done anything? As EWB, it's not our place to change a culture. All we can do is choose who we work with. It's important that this choice is very deliberate. When I started out in Engineers Without Borders, perhaps more naive, I assumed that everyone was equally as receptive or would be equally as receptive to help. But this is not the case. We cannot help everyone, nor should we try. It's important to work with those communities who truly want to benefit not only themselves, but the community as a whole. It's important to ensure that there is wide buy-in from a significant portion of the community, and be sure that all stakeholders stand to gain relatively equally from your service or project. Those were just a few of the kind of idiosyncrasies and lessons learned from that trip. Thank you.
Thank you, Adam, for taking the time to walk through these questions with us. I really appreciate it. I know you had mentioned that this was an important part of your education. I just want to say that this project was also very impactful to me. And a large part of that impact was you. I really appreciated your leadership and your commitment to this project. And it was my privilege to watch you and work with you on this project. Again, thank you for everything you've done. And I'm sure the community of Mbita thanks you as well. Again, thanks. Normally, if we were really having this at a conference, it would be time for question and answer. Obviously, we can't do that. But we're going to try and simulate that with these discussion Padlets. And so here are links to all those Padlets I've been talking about throughout the talk. I just wanted to walk you through the 5 Padlet links we've provided for you. The first one is just for you to type what kind of project you're doing. Just click this little button down here and we are building a dormitory or something like that. Okay. The second one is a little more difficult to use, is where is your project? And so what you're going to have to do is to be able to zoom in and find your project and then put a pin in there. So I'm not going to waste all our time trying to get down to where my project. Oh, I actually might be able to do it. There we go. Our project, close enough. I should zoom in more, but our project is right here. Okay. You got to press the plus sign and then do that. Anyway, click where your project is. It says pick a location right there. Anyway, somehow tag where your project is. The next one is for you to type the best stories from yours. You can say about there was this time when, and fill in the blank. The one that might be of most interest to you is this Padlet with links to resources. And so all the seismic hazard resources on geohazards. If you happen to have a project in Guatemala, here's a thing about Guatemala earthquake hazards. And then here are all the links on Confined Masonry. And this one on the bottom actually has a series of 11 videos walking you through what Confined Masonry is. And then I talk about codes. Many of the projects are in Guatemala. So here's a paper that evaluates Guatemalan seismic code provisions. Here's a link to Eurocode 8, Chapter 8 for the seismic design. And then some papers or web pages from FEMA on seismic codes in the U.S. in case you're interested in what we do here. And finally, the last Padlet is if you have any questions, please post them here and we'll try to respond in a timely manner. We'll look at these every so often. Thanks. It's been our privilege and our pleasure to present this material to you. If you need to get in touch with me, David Mukai, here's my contact information. And if you need to get in touch with Adam, here's his contact information. Again, thank you for your attention and your time. This has been great. Respond to us, please, if you could, if you would, through these Padlets. That would be great. Again, thank you. Have a good rest of the conference. And maybe at a future conference, we could actually meet in person. Take care.